Great, thank you for having me. I'm delighted to tell you about our results from our joint recleansing and clustering analysis. And thanks for your patience in postponing this, I think, twice, so that I didn't have to give another coming soon talk about our results. So I'll try to balance this with a broad overview of why we were doing this and what we found, but also go a little bit into the details of our results and highlight some of the key challenges that we faced. So I'll start with what we're after, which is this end-to-end test of lambda CDM. And then I'll talk about the tools that we need. So we use the dark energy survey and this 3 times 2 point analysis, this joint recleansing and clustering analysis. And then I'll jump into our cosmology constraints straight away, just the main highlights, assuming that most people have seen them, there's not a surprise anymore. And then, because we've really done our best to deliver robust cosmology, and many of the methods that we used were novel. So we had to develop new methods to be able to handle the really vast data set that we had. So I wanted to touch on a few of those and show how we think we push the field forward, not just in statistical power, but also in methodology. And that's important on the eve of Rubin and WFIRST and Euclid. And then finally, I'll come back to our results and show you how they compare to other cosmological constraints before ending with some outlook. So I know this is a cosmology seminar, but a brief introduction, especially for the students. We have measurements of the cosmic microwave background, or the CMB, and this reveals a map of the fluctuations in the temperature and the density from the early universe. The snippet of that is shown in the bottom left from the Planck satellite. And this really is the gold standard cosmological precision, including constraints on the amplitude of primordial scalar density fluctuations, or this AS cosmology parameter. And overall, they find this exquisite fit to our lambda CDM model. Now, after the CMB, the expansion of the universe marched on, and those fluctuations cooled and expanded such that they seeded the large-scale structure in the universe that we observe today. The snippet of that is shown in the right-hand side from a simulation created at SLAC, and we can see there the pattern of this large-scale structure. And from this late-time universe, we can measure sigma 8, so the amplitude of mass fluctuations today. So still measuring how these density fluctuations vary on the sky. Now, recleansing and clustering observations, like the ones that we've made with the dark energy survey, are really excellent at probing our current era of the universe. And this is one dominated by dark energy. And so they measure a very different universe to what the Planck satellite measured from the cosmic microwave background. You're not measuring the imprints of very tiny density and temperature fluctuations, but large fluctuations in an accelerating universe. And so these two measurements are really quite complementary. Now, when we compare our observations that we make in DES, or the dark energy survey, to the same model that is so well measured by the CMB, we create this very beautiful end-to-end test. And that's what we're after. So we're asking, can we use the same picture that fits the seeds of our universe to describe the vast structures that formed 13.8 billion years later? And so we compare our observations of the late-time universe of galaxies and large-scale structure to that same model that is so well measured by the CMB. Now, this is very topical. It's particularly intriguing right now in cosmology because we keep seeing these slight discrepancies or tensions to varying degrees cropping up. And depending on who you ask, it's reason to worry or absolutely not. So measurements of the Hubble constant have gotten quite some attention with 3 to 4 or 3 to 5 sigma differences, and less significant, potentially not worrying at all, but nonetheless intriguing are tensions in the measurements of recleansing and clustering compared to the CMB. Now, what is recleansing and how do we make these measurements that we use in our analysis? So first of all, we're observing the foreground massive objects to be spatially clustered, and we measure their clustering signal. And so you can see these by the gray blobs on the orange grid, and they're distorting the fabric of space-time, or the fabric of the universe. Now, the light from even further away background galaxies journeys across the universe, and their path gets bent due to these distortions. So aside from the clustering of the foreground galaxies, we observe the images of our background galaxies to be slightly distorted. And galaxies whose light travel past the same structures in the universe, like the two on the left-hand side there, they acquire coherence distortions and alignments due to recleansing. And these two observations are what's key to our cosmology analysis that we just released. And I can show you that in a little bit of a different way on this side. So now we have our background yellow galaxies on this snippet of the simulation box, and they travel through the large-scale structure past the foreground red galaxies to the image plane on the right-hand side. And the observed shapes in the image plane, so the observed shapes of the yellow galaxies, will appear lensed or shaded. We make statistical measurements of their correlations, and these carry the imprint of the large-scale structure that the light passed through. For the foreground red galaxies, they're tracing the web of the simulation box or the underlying dark matter structure, and we measure their spatial distribution or how clustered they are, and it tells us about the cosmology as well. So we have two fields that contain cosmological information, the Scher field from the background and the galaxy density field in the foreground. And for any field with a mean zero like these, a simple way to quantify the fluctuations is to measure the 2-point correlation functions. So that's exactly what we do in DES. To compute the weak lensing correlation function from our yellow background galaxies, we need a measure of their positions and of their shapes. And we measure the correlation between pairs of shapes as a function of their separation, their angular separation. Now, on the other hand, we compute the clustering correlation functions from pairs of positions of foreground galaxies. Now, to model both of these signals, we need to understand how far away the galaxies in the samples are. So they're redshifts, and we measure the photometric redshift distributions of these galaxies. And this allows us to directly relate our signals of the underlying structure of the universe to the underlying structure of the universe. And so we're particularly sensitive to two cosmology parameters, omega matter and this sigma 8 parameter, the amplitude of fluctuations. Now, in reality, we don't just have one source sample or one background sample and one lens sample. We divide each of these samples up into redshift bins. So we do our analysis tomographically. And that allows us to enhance our signal to noise and probe the evolution of structure with redshift. And that gets us at dark energy. Now, the cosmological workhorse for DES we call the 3x2 point. And that's because we're combining three 2-point correlation functions. So the shape correlation of the sources of the background galaxies, that's cosmic Scher, and that's really the core of the analysis. The position correlation function of the lenses is galaxy clustering, and the cross correlation of the two galaxy-galaxy lensing ties the galaxies to the underlying dark matter distribution. And you can see in the plot on the right-hand side that the cosmic Scher and the 2x2, we call them, so we call the clustering plus galaxy-galaxy lensing 2x2. So in the end, we have two sets of contours. The cosmic Scher and the 2x2 constraints shown there in blue and yellow respectively, they have a bit different degeneracy directions, and so they're complementary. So of course, when we combine these measurements, not only do we get enhanced precision because of breaking those degeneracies, but the combined analysis allows us to self-calibrate and constrain nuisance parameters that hinder each analysis on their own, each measurement on their own. So it really lets us maximize on cosmological information. And you can see in that plot as well that with these measurements, what we're most sensitive to is a combination of omega matter and sigma 8, this S8 parameter that people have been talking about, whether there's a tension there or not. And so that's just the smallest direction across that plane. Now, right now, the Dark Energy Survey provides the current state-of-the-art in lensing data. This was a 6-year survey, and we finished collecting data. I think I did the second to last observing run a couple of years ago here at the Blanco telescope in Chile. And the goal of this survey really is, unsurprisingly by the name, to constrain the dark energy equation of state. And we do that with weak lensing, large-scale structure, but also with supernova and cluster counts and BAU. So those will be released in follow-up analyses. Now, we used this survey to map 5,000 square degrees of the sky in a few photometric filters with a 3 square degree field of view camera. And we use this wide, deep survey strategy. So I won't go into too much detail of this later in the talk, I will mention it, But this is really key for our year 3 analysis. We have a few fields where we have very deep observations, and they're chosen to overlap other data sets on the sky, and they really helped us understand our survey better and calibrate our data better. Now, the year 3 data set has really grown to impressive precision compared to year 1. So now we're mapping the full 5,000 square degree footprint on the sky, and we're going to about half depth of the survey's capability. And our cosmology catalog in the end had a staggering 100 million cosmology good galaxies. So we started off with 400 million objects, and we refined that down. And this survey is 3 to 4 times bigger in area and number of galaxies compared to the year 1 data set from DS and the next leading recleansing experiments. So here's our footprint in all its glory on the sky. Our footprint is in the south of the sky. And yeah, this plot is very beautiful. So beautiful, in fact, that a few of us made puzzles out of it to get us through the pandemic. So you can see here, it's one of those fancy puzzles with very strange shapes, and it even spells DES in some of the shapes. So I can point you to order your own DES puzzle if you really want afterwards. Now, before I show you results, I need to say that DS is really an enormous team effort. So I feel very fortunate to be part of this, and it's work that I certainly could not do on my own. Our key project team is from all around the world, as seen here. And a team effort from a diverse group is really what it takes for this good survey science and innovative survey science for this team to work well together. So here's just a few pictures of the main people involved in this analysis. And so you can see quite how many cooks it takes to make the soup good. Now I will jump into the results, and I'll use this to frame and motivate the challenges that I'll talk about later on. So we have 3 2-point correlation functions and 2 measurements, so cosmic share and the 2x2, which combines the other 2. Here are cosmic share and or weak lensing results. So on the left-hand side, I'm showing the correlation functions. So as I said, we measure the correlation functions of galaxies across redshift bins and with itself, with its own redshift bin. So to orient you, there are 2 correlation functions for cosmic share, psi plus and psi minus, psi plus on the left, psi minus on the right. And you're seeing lots of panels because we have 4 redshift bins, and we cross-correlate each bin with itself and with each other. But what you can take away is that the black data points are our year 3 measurements. The yellow shaded region is our year 1 statistical error. So really, I mean, this is clear from the number of galaxies we had, but we really did beat down that statistical error. And the green line is the best fit that we found in the end in our analysis. And the lower panels are the difference panels between the model and the measurements. And the cosmic share measurements really are an exquisite fit to the best fit model. So these are the highest signal to noise lensing measurements to date. And on the right-hand side now, I'm showing you the cosmology that you get out of this. So the cosmology constraints are shown in green. In yellow, we have the Planck CMB constraints. And in black, we also define from our analysis this lambda CDM optimized analysis. So this is not the result that we used for unblinding, but it is absolutely safe in lambda CDM. So what happens is in lambda CDM, we can push to smaller scales safely with our same rigorous method of defining what scales to use. So on the left-hand side, you can see this blue shaded region. We discard all of those measurements because we think we cannot model them safely, and this throws away a lot of constraining power. So we pushed that back a bit more to give you the darker blue shaded region, and that gives you your lambda CDM optimized analysis. And it really improves the precision of the cosmology constraints by about a factor of 1.5. And so we assess the consistency of the lensing results on their own with Planck. I'll talk later on at the end about how we quantify this in more detail for the 3 times 2 point. But formally here, we find consistency in the full parameter space at the level of about 2 sigma. And with the lambda CDM optimized analysis, we add more information and we push towards Planck, even though our error bar shrinks. So it stays about the same, that consistency. Similarly, for the other measurements like galaxy RT lensing and galaxy clustering, the data vector is shown on the left-hand side. So again, just the main thing to take away is that difference panel where you can see the fits of the measurements to the model. The gray regions are discarded measurements again, and that includes the 2 high redshift lens bins. So this is a decision that we made after unblinding. I'll say a bit more about that later on, but we didn't think that these 2 bins the measurements were safe to use, so we discarded them. And overall, we find the 2x2 constraints to be consistent with year 1, also consistent with Planck, and so they kind of sit in the middle of these 2. Now on this plot, I'm just showing those 2 measurements now on top of each other. So the cosmic share you saw before is in blue and the 2x2 is in orange. And these 2 measurements, you can see their complementarity. The 2x2 is more sensitive to omega matter, and cosmic share is more sensitive to that S8 parameter. And the requirement for unblinding our analysis was that these 2 measurements were consistent. And so that was satisfied on our unblinding coil. We revealed the consistency and we saw that we passed. And so we can combine and look at the 3 times 2-point results, which is shown in that black contour there. And I'm quoting the best fit parameters that we find on the right-hand side. And these are about a factor of 2 improvements compared to Y1 in the sigma 8 and omega matter plane. We can compare the 3 times 2, our low redshift 3 times 2 result to that high redshift Planck result. So that test that I started off talking about at the beginning of the talk to test our lambda CDM model. And we find no significant evidence for inconsistency between DES year 3 and Planck. So again, I'll quantify that later on, and I'll also talk about our constraints in WCDM and our comparisons to other data. But one comparison that I did want to flag now is that discussion that I alluded to about tension in this S8 parameter coming from all the weak lensing surveys. So with the most powerful lensing data set with DES year 3 in our full parameter space, we do find consistency with Planck. And that's true if you're talking about just the cosmic share results, the lensing results on its own. So you can see those on the left-hand side in the omega matter and sigma 8 space. Those are from cosmic share alone. And then on the right-hand side, it's a compilation of all of the latest results on this S8 parameter. So DES year 3 is the green underlined ones. That's corresponding to the one on the left. At the bottom of that, there's the weak lensing plus large-scale structure constraints as well. And the trend there really is pretty fascinating that they're all low. So even though our result is consistent with Planck in the full parameter space and in that parameter alone, it really is quite intriguing and frustrating almost to add our new data point, the most powerful data point that on this plot, and find that it's consistent on its own with Planck, but it does continue this peculiar trend. It is important to note that our results have shifted towards higher values of S8, so towards Planck compared to year 1. And the most important thing about this plot, I think, is that it is very difficult to compare these results quantitatively. So the different lensing surveys right now are using different model choices, different scales, and different statistics. And so to really assess this tension from all lensing surveys and to see if this continuing trend is powerful or not, or is significant or not, we really need to do a joint analysis with consistent choices. And that is something that we're pursuing in collaboration with the other surveys. Now, I'm going to change gears a bit and tell you a bit about our process. So this slide is overwhelming on purpose, and that's because it is a pretty hefty roadmap to deliver a validated and robust data set that enables our precision cosmology or any of the other countless analyses that will benefit from the DES data. So 3 times 2-point analysis in particular is complex and multifaceted. And this is just a top level overview of some of the main parts of the process to convey that. So we're starting from images on the left to cosmology parameters on the right in red. And each bubble has kept a team busy for a couple of years. So we have analysis teams, and I co-coordinate 3 of them. But this expanse of this work is really evidenced by the suite of published papers that we've kind of bombarded arXiv with. So here I'm bolding all the early career authors, and that's almost all of them. And to me, that's one of the most impressive parts of our year 3 analysis, that we really have ECS members kind of steering the ship. And of course, we were coordinated by Michael Troxell, Elizabeth Krauss, and Scott Doddleson. Now, I wanted to guide you through just 6 of the challenges, there are more than 6, for our analysis, and how in DS we really thought we bolstered the methodology. So I'll just give you a flyby tour of some of the steps of this flowchart to break it down. So starting with the wide field images, we need to create a shear catalog. So measuring the shapes of galaxies is a lot more difficult than it sounded at the start of my PhD. The galaxies that we're dealing with aren't quite these picturesque spirals like on the left, but the fuzzy blurry ones on the right. And that's because that pretty picture of a galaxy passes through the large scale structure and acquires that desired cosmic shear signal, which is about a 1% effect. And then it carries that light all the way to Earth, this very tiny signature that we're after. But that signature gets ruined by our atmosphere, our telescope, and our detectors. So it gets blurred and pixelated, and then there's noise. And so it really is quite a challenge to remove those unwanted point spread function effects, or the PSF effects. So for DS year 3, we had a new technique primarily developed by Mike Jarvis called PIF, to remove that point spread function, so to model and account for the effects of the atmosphere. And that was really advantageous for us. I think it made us a lot more confident in our shape measurement. We extended the suite of shape catalog tests. So we really had many more tests compared to what we did in year 1. And so those are published in the papers that I highlighted there. And in the end, we whittled down our object catalog to 100 million galaxies, or just over 100 million galaxies. And so these are galaxies that have passed all the extensive validation tests that we required. Now, aside from shape measurements, what I said you also needed to do your recleansing is a measurement or an estimate of the redshifts of our galaxies. And this is widely talked about for the last few years, in particular for recleansing. And that's because it's pretty challenging. Why is it so challenging? Well, photometric surveys don't get the beautiful spectra for each galaxy, like the lines, the black lines shown in that figure, but just observations in a small number of photometric bands. So you can imagine, with limited observations, there's a huge amount of degeneracy with the galaxy type and the galaxy redshift. So if you look at this example in the plot, if I only had observations for these 2 galaxies in RIZ, which is the case for DES, you would not be able to distinguish or estimate the correct redshifts for these 2 galaxies, because there's so much degeneracy with their type. So we really have to do quite a lot of work to get accurate redshift distributions. And so for the DSY3 analysis, we built an entirely new framework. So we had a large team working on this, and we prioritized 4 key aspects. One was that we had this deep wide survey strategy. So we used the deep fields that I mentioned before to help calibrate. So those, because of the fact that we only have 3 bands, the deep fields were helpful as like a stepping stone between spectroscopic information and then 5,000 square degrees of 3-band data. So this new survey strategy was really key for us. And then whatever the method being used, there's a lot of debate on whether you can, when you're estimating your redshifts with colors, there's a lot of debate on whether you want to use spectroscopic or photometric redshifts. And we wanted to make sure that we were robust to this choice, given all the discussions in the community, because neither on their own is perfect. Both choices have flaws in them. So we kind of used all the information that we had together. We devised a way to do that. Then the third step is, usually for recleansing surveys, you have multiple methods to estimate these redshifts. And you kind of just compare them at the end and say, okay, well, they look consistent, so we did a good job. But we wanted to go a step further than that for year 3, where we had our 3 methods, and once we assessed their consistency, which is what's shown at the bottom in the contours, then we combined all their information. We combined their likelihood, so we could really get tight constraints on our redshift calibration. And then we accounted for uncertainties in kind of a new way, where we accounted for the full uncertainty of the redshift distribution, and characterized all the sources of uncertainty that we could think of. And this was an enormous effort, primarily led by Justin Miles, who's a grad student at Stanford that I co-advise with Daniel Gruen. Now, here is just showing the stability of our cosmic share results to all the different dials you can turn in your redshift calibration. So you can use a different training sample, you can use only photometric or only spectroscopic. You could use only one of the three methods. You could not account for the uncertainties at all. And what we found is that our results are very stable to all different, to even the most extreme choices in our redshift calibration. So on this summary plot, the empty circles, we didn't expect or require them to agree. You can see the last one is entirely switching off the uncertainty on redshift calibration, and we still get pretty stable results. So that gave us a lot of confidence. Now, the other challenge, the third challenge is now that you have your shapes and you have your redshifts, you still have to calibrate these to account for effects like blending. So with our surveys now, this is what a lot of observational lensing people are worried about as we push to deeper images and deeper data. So this will be overwhelmingly true for Rubin. Almost all of our galaxies are really just a clump of galaxies that happen to be overlapping as they're projected on the sky. So how do you measure the shapes and redshifts of these 5 or 6 galaxies in this image? And how do you disentangle their weak lensing signal when they're all coming from different redshifts by chance? So this is an unavoidable consequence for deep data and something that we worry quite a lot about. For DSER3, like other analyses, we rely on image simulations to understand this. So we developed an entirely new suite of image simulations, and these are multi-band and multi-epoch, which is new. And we tried to model and understand blending in a new way, and account for it all the way to our cosmology parameters. So we saw that blending is almost always, at least for me, I always thought of it as a shape measurement problem, but we kind of showed that it's just as worrying it has just as worrying an impact on your redshift calibration. It really just kind of messes up everything. So we modeled it in a new way and accounted for it in the cosmic share analysis. And I think that's another place where we really kind of pushed the methodology forward. And really, we've just kind of cracked open this problem with the new set of simulations. I think we have a lot more work to do there. Now, building a lens sample is also challenging. So we have to pull out from our catalog a foreground lens sample that we use for galaxy clustering and for the galaxy lensing. And this is difficult because you have different selection effects when you're pulling out a lens sample, and you also want to trade off the statistical power, so how many lenses you can get, versus how good you understand their redshifts. So when you're measuring clustering, you need to know the redshifts pretty well. And so to get around that in DS, we had 2 lens samples for year 3. So we used red magic, which is what was used for year 1. So these are luminous red galaxies that are selected in a very specific prescription, but their redshifts are well known and well calibrated. And then we also came up with this new sample published in Anna Pordon's paper called the magnitude limited sample. So it's a bit more simple of a selection, but you get a lot more galaxies that way. And you trade off, as I said, the amount of lenses that you get with the photometric redshift error. So you get 3.5 times more galaxies in red magic, but they have 30% wider uncertainties on their redshift, and it's a trade-off. I think this is one of the most powerful parts of our analysis, that we had 2 lens samples, and that turned out to be especially true. But it was also the puzzling aspect of our analysis for a long time. So we unblinded in October on US election day, and we kind of got stumped in the comparison of these 2 lens samples for quite some time. So you can see why on the right-hand side. The dashed contours are showing so in blue, the dashed contour is the cosmic share contour. In orange, the dashed contour is the 2x2 result from red magic. And you can see that it's pretty offset from the cosmic share results. Interestingly, in red magic, the 3 times 2-point result, so the combine of that orange and blue, is shown in the dashed black contour, and it is in exquisite agreement with our magnitude limited results. So in 3 times 2, these 2 lens samples give consistent cosmology results. This is what was intriguing. Everything was fine in 3 times 2, but when you ripped back the cover and looked at the 2 by 2, the results between the 2 lens samples were very different. So we could see that I can talk more about that in the questions if you want. But this is really the power of the 3 times 2-point analysis, that it can self-calibrate itself. So in 2 by 2, we have strong evidence that what's happening in red magic is uncalibrated systematic in that lens catalog. But when you combine it with the cosmic share anchors down your S8 constraint and helps calibrate out the systematics. Now, one aspect of that is that we defined this when we were going through our investigative process. We defined this X parameter. And what we can see is that in red magic, in some way, we have some decorrelation between the galaxy clustering and the galaxy-galaxy lensing. So it's essentially that the 2 measurements want different values of galaxy bias. And so that would be, some sign of stochasticity if you didn't believe it was a systematic. But as I said, we have pretty good evidence that it is an evidence of an observational systematic residual in the catalog. And what we've made sure is that the 3 times 2-point results are consistent. This X parameter that resolves whatever weird is happening in this lens sample, it is not correlated with the lambda CDM cosmology parameters. So we think that the lambda CDM cosmology parameters from both lens samples, so from both 3 times 2-point results, are robust. And the magnitude limited doesn't have any evidence of this inconsistency, and that's our fiducial lens sample. Now, of course, the fifth challenge is the modeling. So of course, galaxies are complicated. They're not just the blurry images that we measure, but they have galaxy bias, complex baryonic processes, and they can be intrinsically aligned. So we have to account for all of these different effects in our model. And so what we end up with is a very large parameter space. We have parameters for galaxy bias, for galaxy magnification, for intrinsic alignment parameters. So overall, we have 9 astrophysical parameters. And we account for nonlinear bias and baryonic effects by throwing out those small scale measurements, as I showed before when we were showing the results. So overall, when we do our MCMC, there's a lot of parameters really to marginalize over. One of the tests that I wanted to flag here that we did in my paper is as a nice internal consistency check for your model. You can not only do robustness tests with alternative models, but look at the internal consistency of subsets of your data. So for example, do I get consistent results in high redshift and low redshift cosmic share, or small scales and large scales? And what we found is that all of these tests passed the criteria that we set, and we found consistent cosmology for the cosmic share. Now, finally, I wanted to just mention blinding, because this is what the sixth challenge that I wanted to flag, because it really underpins our analysis. For DES year 3, we really went with very rigorous blinding of our analysis. We knew what kind of precision that we were going to have with our data, and so we wanted to be extra careful. So we had 3 steps of blinding. We blinded our catalog, so that even if I made a cosmic share measurement and ran an MCMC on it, the shares were shuffled so that you wouldn't really get a sensible answer, or it would be sensible, but it would be shifted. And then we had this nice scheme developed by Jesse Murr, where when our pipeline computes our correlation functions, it automatically gives you these blinded results. So it will take your correlation functions, work out what cosmology they would be at, shift the results in WCDM space, and then give you back correlation functions for that shifted result. And that was really nice, because then we could make sure that our 3 measurements were blinded consistently, and would give a somewhat sensible answer. So we could do all our internal consistency checks and still preserve that blind aspect. And then we just shift our parameters in posterior space. So we never actually saw the result. And this was really rigorous. Up until unblinding day, we never looked at, obviously we never looked at unblinded cosmology constraints, but we didn't look at internal consistency of the three measurements. We didn't look at the size of the constraining power. So we really went, I think, a few steps forward in how much we blinded our analysis here. And that had challenges. It took us a long time to get our results out after unblinding. But I think it's really good for the field. So long before getting to cosmology constraints, there's a lot to talk about, and it's an enormous effort behind the scenes, and that's really what's important. I think in DES Year 3, we did a really good job of tackling these challenges in each of these components and pushing it forward. So now I've tried to show you a bit how the pie is made. I'll go back to this plot for showing our 3 times 2-point results. So we found consistency in cosmic share and 2 by 2 and combined for our 3 times 2-point black constraint here. And this is showing the qualitative agreement with Planck. Showing that again, the comparison to Planck now on the right-hand side, so the omega matter and the sigma 8 plane at the top, on the same omega matter S8 plane at the bottom. So visually, we find better agreement with the 3 times 2-point and Planck than compared to year 1. So despite the fact that we have pretty substantial improvements in the precision on both the DES side and the Planck side compared to the year 1 analysis, we do start closing the gap on the tension there. And this is still unchanged even when we use that lambda CDM optimized analysis with more small scales that gives you, for 3 times 2-point, about 20% tighter constraints. They shift towards Planck again, so that same level of agreement is preserved. And so we compute consistency with shifts in parameter space, but also with the Bayesian evidence. So we find the parameter difference for S8 to be 1.5 sigma. And in the full cosmological model space, a suspiciousness of about 0.7. And we predefine before unblinding what our consistency level would be, what we would tolerate. So because we found through 3 times 2-point and Planck to be consistent, the combined constraint is shown there in orange. We also compared our results to those from external low redshift measurements, so supernova data, BAO and RSD, supernova from Pantheon and Pan-STARRS, and the BAO and RSD from EBOS. And this is the results here. So you can really see the complementarity of these data sets. The supernova BAO and RSD is shown in orange, and that does really does a very good job of constraining omega matter. The DES 3 times 2-point is again in black, and it adds substantial information in that AS or S8 parameter. And again, Planck is in green. So I should have said AS is on the top now and S8 at the bottom, both as a function of omega matter. And I really love seeing how these kind of fan out around each other. And so the 3 times 2-point adds in that AS or S8 parameter, but that allows you to break degeneracies in the correlated parameters, and so it does hammer down your omega matter constraint. And these external low redshift data sets really complement the DES weak lensing and large scale structure information by probing the growth and the geometry of the cosmological model in fundamentally different ways. So we find better agreement between all of these low redshift probes and compared to Planck. So the 3 times 2-point is in black. The external probes, the external low redshift probes are in orange. We combine those two sets to give you the purple, so that's a full low redshift measurement. And when we compare that to Planck in green, we find better agreement, well, even better agreement. So it warrants us to combine again for a final result of which the parameters are quoted there in the orange block. And now here's just showing these results in WCDM. So this is a model extension equivalent to a cosmological constant when W is equal to -1. And we find no preference for a free dark energy equation of state or no preference for anything beyond lambda CDM when we consider WCDM. So similarly, the external low redshift data really probes W quite well, and the DES 3 times 2-point adds in this S8 parameter, and that breaks a bunch of degeneracies and gives us slightly better constraints. Now, interestingly, we also looked at the H0 tension. So we can constrain the Hubble parameter using a combination of BAO, BBN constraints and the DES 3x2 points. And when we use the BAO and BBN, those give you the orange constraints. So those are external to DES. DES 3x2 point adds just a little bit. So now we're adding the orange and the black. Orange, sorry, with the 3x2 point to give the black. And we get a constraint that's about 3 to 4 times more powerful than any current local measurement of H when we combine with Planck as well. And so we used here a local prior from shoes to be able to get this constraint. And what's shown here is, of course, that it still has a 4 sigma discrepancy with the shoes measurement. Now, going back to this puzzle right before I wrap up with the summary of the weak cleansing results, I should have said a little bit more about this. Sorry about that. So the orange vertical bar is the CMB Planck result, looking at the right-hand side plot. Previous results from the kids team are shown in blue. So the kilo degree survey has the widest coverage. It's not as big as DS and it's not as deep as the Hyper Supreme Cam survey in red, but it has the largest wavelength coverage. So I actually did my PhD with the kids team and then swapped to DS while I was in the US. So the kids is in blue, HSC is in red, and DS is in green. And when you look at the lower results from the 3x2 point or the combined recleansing and clustering analyses, that recent result from Heyman's 2020, the kids 1000 plus BOSS plus 2DF lens, is that nice small blue data point. And the DES 3x2 point optimized result is shown here as well. I mean, this is a matter of opinion, but I find this both intriguing and frustrating. We do find overall consistency with Planck, but I am keen to see how we can put better constraints on this plot to pin down whether this S8 tension is really something there or not. And so what can we do to better understand what's happening? As I said, we're working on a joint analysis with the kilo degree survey, which I think will be fantastic to see how these. So we're going to make sure that we have consistent analysis choices and really remove all of the things that make these data points wiggle a bit. And of course, give a combined results, which will have a lot higher precision. We've already started working on DES year 6. So this will go to double the depth of what DES year 3 had. And that will be very exciting. Now, when we double the depth, you have to think about what will be, how will that work? Well, our redshift and our blending methods will be stress tested with this deeper imaging. I think that will be challenging, but really is just a step towards the stage 4 surveys where they're even deeper than the DES year 6 data will reach. And I added this plot here, the omega matter sigma 8 contours, where in my cosmic share paper, I was looking at what was limiting the precision of cosmic share. So could you get more out of your out of the same data? With what do you need to improve to maximize the information from your data? And what we found was that we're really limited by the theoretical systematics. So if you compare the blue, which is already the optimized result, to the red, which is when we fix accounting for these astrophysical effects, we almost get a factor of 2 improvements in our constraining power. So I think, for year 6, what I'm really looking forward to is trying to safely make more aggressive analysis choices in our modeling. And that will help us add tighter data points to this S8 compilation plot. The other thing that I just wanted to flag that I've been looking at since we finished DES is there is this lensing is low that has been discussed as a discrepancy between galaxy-galaxy lensing and galaxy clustering. And this is presented in Liotho et al. 2018. And this is a 40% effect, but it is on very small scales much smaller than those that we use in our DS analysis. So there's been questions about if that's tied to this S8 tension or is it tied to this X problem that we found in our red magic imaging. And so this is something that I've been looking into. And what we're seeing is that we are starting to close the gap on that lensing is low as well. And I think what we will find is that, well, my hunch is that what we will find is that modeling uncertainties on those small scales will encompass this discrepancy. And finally, we'll have an analysis looking at the extensions to Lambda CDM, and that's coordinated by Agnes Verde and Jesse Moore, and should be on the horizon. Well, it should be out in not too long. So to summarize, I'll leave these up here and take any questions.